Hello everybody and welcome to our Brain Vision Analyzer webinar on independent component analysis. Let me please introduce ourselves to you. My name is Michael and with me is my colleague Bastian. Let me show you now the outline of today's webinar. The first part will be devoted to ICA theory, where we will check out the rationale behind using ICA methods and look a bit into the mathematics of the method. The second part will deal with applying ICA, and I will lead you through all steps from pre-processing to back projection and give you some information about the available options in Analyzer. Our webinar today is about ICA in general, but I will also cover ICA-based ocular correction, as it is one of the most prominent use cases for applying ICA methods. We will then go through some open questions, and I will conclude with a summary and some literature recommendations. So my goals for today are to show you how ICA works and what are the prerequisites, what are the options for ICA in Analyzer, and what are the classical use cases for ICA. The expected learning outcomes for you would be to learn how to use ICA or Ocular Correction ICA in Analyzer and make an informed decision about which options to select. To interpret the outcome of an ICA analysis, namely the independent components, and how to integrate the results into your processing pipeline. So let's start with some theoretical basics before we have a look at Analyzer. Imagine we are recording an orchestra playing a symphony. We place several microphones on the stage and record the complete concert. In the end, we will have as many recordings as there are microphones. What we would like to have are clean recordings of the key players. However, the sound of the orchestra spreads across the whole stage. So even if we place a microphone right in front of the strings, it will also record the drums or the sound of the brass section. So all recordings therefore contain signal mixtures instead of only one signal source. They are contaminated by several instruments and potentially also by noise. What we want to do is to unmix the signal in order to extract the key players and reduce the noise. Independent component analysis offers this opportunity. It can unmix the signal mixture stemming from different independent sources. If an ICA is meant to succeed at this unmixing procedure, several theoretical assumptions need to be met. I will get back to them in more detail, but some major assumptions are: the signal has to be a mix of independent sources with temporally independent time courses. Here, every instrument would need to have their own sound profile and to play their own tune. Furthermore, the recording sites as well as the sources of the sound have to be stationary. This is given if the players and the microphones stay where they are throughout the recording. Now let's transfer this example to brain activity and EEG recordings. We assume that there are different sources of brain activity. These would be the different instruments of our orchestra. Each of them has their own independent time course. We record this activity with electrodes on the scalp surface. These would be our microphones. Because the signal from the sources propagates throughout the cortex, as the sound would spread on a stage, each of the electrodes records a signal mixture stemming from several sources, including brain activity and noise. Again, for an ICA to be successful, the time courses of the sources needs to be independent. And the sources as well as the recording channels need to be stationary. So with ICA, we can extract statistically independent signals from EEG data. Why would we want to do this though? One possible answer would be that we could extract only those components that we are interested in. And another answer would be that we would identify components representing noise or artifacts. And we can use ICA to remove them in order to clean up our signal mix. I have already shortly tackled the mathematical assumptions presumed by ICA, but when talking about the concert example, let's sum this up in general. The extracted source signals or independent components have a characteristic time course which is statistically independent from any other signal. The core point here is statistical independence, which we will have a look at later. The generators of the source signal as well as the sensors need to be stationary throughout the recording. This assumption should be fulfilled for specific EEG signal parts, as for example non-neural noise sources or the EOG. But we could also assume it for specific physiological processes that are well defined by an ERP with a fixed neural generator. This assumption is the main reason why we can generate component topographic maps, as the projections from components to sensors are fixed. The mixture of the source signals to the mixed EEG signal needs to be linear, and propagation delays can be neglected. The source signals or independent components cannot have a Gaussian probability distribution. Why this is the case, we will see later. As ICA is a blind source separation algorithm, it can be used in principle for any signal type. Blind source separation means that the algorithm does not need information about the nature of the source signal or the mixing process. An important point is that the independent components are source signals in a statistical sense. They thus do not map directly to physiological processes. Finally, and importantly, the number of sensors and the maximum number of source signals is equal, and I will show you why this is the case. But this fact makes ICA a complete decomposition method. So in principle, our human EEG signals fulfill these mathematical assumptions, and that's why we can use ICA to unmix or decompose the signal into its sources. Let's check out the math in detail. In this formula, X is the original data in a 2D matrix. It could, for example, be an EEG signal that we recorded, and then the unit is voltage. The 2D matrix hence consists of channels by data points. Each of the channels in the rows contains a linear signal mix stemming from several sources, like different brain activations or noise. ICA unmixes the signal into independent components, which end up in the component matrix. Here, each of the rows contains one component, meaning one statistically independent source that was extracted from our original data mix. These are not to be confused with the real data and don't have a unit. Columns are still data points though. We can inspect the time courses of these components to identify artifacts or sources of interest. To achieve this transformation from data to components, the ICA has to generate a weight matrix or ICA matrix. This matrix contains a set of unmixing weights W for each channel component combination. Multiplying this weight matrix by the data matrix results in the component matrix. This implies matrix multiplication. Thereby, the first row of the weight matrix, which contains one weight for each channel, is multiplied by the first column of the data matrix, which is the first sample point of each channel. These multiplied elements are then summed up, and they result in the first value of the first component in the component matrix. Multiplying the first row of the weight matrix with the second column of the data matrix results in the second data point of the first component, and so on. Due to this computation, the maximum number of components we can extract is limited by the number of channels that we recorded, even though we don't know how many statistically independent signals actually contributed to the mixed signal. There are a few preconditions on the data when you want to calculate ICA, and some of them can be influenced by you. This is first of all the number of channels used for decomposition. As we just learned, this number determines the maximum number of components. In case that only a small number of channels is used, but a signal mixture contains a greater number of true source signals, it can happen that valuable information is lost due to underfitting. There might just not be enough independent components available to represent all source signals. Therefore, it is generally advisable to feed a larger number of channels, like 64 or more, into ICA. But especially strong source signals like EOG activity can usually be decomposed well with less channels. If the data contains interpolated, equal, or constant channels, these should not be fed into ICA. The same holds for reference channels. The reason for this is the linear dependency between channels, for instance between scalp channels and a reference electrode. The same holds for average reference data. However, it is okay to disable at least one channel that forms the reference to resolve this issue with the linear dependency. A second rule is that ICA works better if the data is clean, to prevent that independent components are used up by source signals that are only transient. I will go into more details about this later. Lastly, ICA needs sufficient data for training. There is a rule of thumb how many data points to use at least, depending on the number of channels. For 60 channels, for example, you have to calculate 20 times the number of points, the number of channels squared, so 20 times 60 times 60, which is 72,000 samples. With a sampling rate of 1000 Hertz, this would be 72 seconds. This is of course only the minimum that is required, and we would always recommend using more data so that you can adequately represent the activity that you want to decompose. So use something that is representative. Then there's also some pre-processing that has to happen before ICA, and therefore those steps are already included in the transformation analyzer. Those steps are demeaning and sphering. Demeaning will subtract the offset between channels for ICA. However, note that the offsets are again added back to the data after back projection. Sphering is considered a prerequisite for ICA and reduces the dimensionality of the data by means of PCA to cope with linear dependencies. It is still recommended to avoid introducing linear dependencies as mentioned before, but consider the sphering as an additional security check in case there might be dependencies that you're not aware of, for example, from gel bridges. So, having identified the ICA weight matrix, we can unmix the signal into statistically independent sources. This unmixing from the data into components can also be reversed with the inverse of the ICA weight matrix by multiplying the extracted components by the inverse ICA matrix. And then we can transform the signal back into channel space. And this is called back projection. If we don't exclude any component before back projection, the original data will be restored completely. Let's take a closer look at these inverse ICA matrix. Within the inverse ICA matrix, each column refers to one component and contains one weight per channel. If we have channel coordinates available, the inverse weight matrix can inform us how a component can be mapped back onto the channels. As we have one inverse weight per channel in each component, we can plot one topographic map per component. Note though that these maps are stationary throughout the recording, which means a single map per component that does not change over time. The component maps indicate to some extent which channels were mostly affected by a component. Please note though that the absolute values of the maps are arbitrary, and different component topographies should not be compared numerically. Also, both warmer and colder colors indicate larger weights, so the polarity could just as well come out inverted due to the way the weights are extracted. Any of these components can now be removed before back projection. For instance, if we conclude that the component relates to an artifact, given its topography and its time course. This can be done by setting the inverse weights to 0 before multiplication with the component matrix. If a component has 0 weights, its contribution to the data is removed. This means that the influence of the underlying signal, and thus the artifact, are excluded from our mixed signal. Now we know how the ICA works in general, but what we do not know yet is how we get our ICA weight matrix W. Imagine the collection of all possible ICA matrices as a landscape with plains and peaks, whereas the highest peak would mean maximally possible independence for the component result. We can start with some arbitrary initial values for our weights in a matrix W start, and optimize the ICA matrix from there in such a way that we get to a better solution in every step. Just as a side note, complete independence can never be achieved with finite data, which is the case for EEG recordings, which means we go for the maximum of independence that we can get. The algorithm would thus climb up in every step to the peak of the landscape, would sometimes also descend into a valley, and continue again its climb to the top. This means that the optimal ICA matrix W is determined based on an iterative fitting procedure. Fitting stops if a certain criterion is met. In this case, maximal temporal independence. In our landscape, we would then reach the highest peak at W max. However, if we do not get there, for example, because the algorithm has too many difficulties in climbing up, the optimization will stop at W end if a maximum number of iterations has been accomplished. The question is, which statistical property should we choose that reflects statistical independence? This means we need a measure to quantify when we are at the peak W max. First of all, independence places stronger constraints than simple correlation does on the probability distribution of two signals. Independence means statistically that the joint probability density functions of two signals x and y can be predicted from multiplying the two marginal probability density functions of x and y. In other words, this just means that the two signals x and y are completely unrelated to each other. There are a few measures that can be used to assess independence between two signals. For example, negentropy, kurtosis, mutual information, or maximum likelihood methods. The first two, negentropy and kurtosis, are highly tied together, since if one is maximized, the other one also goes up. They can be used to assess how Gaussian a distribution is, which means that you can measure deviations from a normal distribution. Let's now pick out one of the measures which can assess independence to make it a bit clearer what exactly happens. I will explain this based on kurtosis, as this measure is easiest to grasp in a graphical approach. Following the central limit theorem, a signal mixture should result in a Gaussian distribution, also when the individual source signals do not have Gaussian distributions. As examples, I show here a signal mixture and two source signals, line noise and a pure EEG signal. The signal amplitudes can be plotted as a histogram, which depicts the probability of each amplitude. The integral of the distribution can therefore be described as probability density function, which is depicted by the red curve. I mentioned before that kurtosis characterizes the Gaussianity or peakedness of a distribution. As you can see, the probability density function of the signal mixture is Gaussian. The kurtosis of this distribution is 0. The other source signals show non-Gaussian distributions. Line noise shows a flat distribution with a negative non-zero kurtosis, while the EEG signal shows a peaky narrow distribution, which has a positive non-zero kurtosis. Now remember independence. If considered from a distribution perspective, the joint probability density function of two independent signals needs to be non-Gaussian, like the distribution of source signals shown at the top is non-Gaussian. This is depicted in the brownish and peaky joint distribution of the two signals on the bottom right. Kurtosis, or another suitable measure, can be used to assess the non-Gaussianity of this distribution. What does this imply for ICA? ICA can only extract non-Gaussian independent components, which means source signals with a non-zero kurtosis. Transferred to our example signals, this means we could extract the source signals of line noise or pure EEG from the signal mixture. And how do we get from our Gaussian distribution of the mixed signal to a non-Gaussian distribution of independent source signals? A linear transformation has to be applied in order to modify the joint distribution in such a way that the joint distribution in the end is as non-Gaussian as possible. And this process is in fact the iterative fitting procedure for the ICA matrix W. In Analyzer, two ICA algorithms are implemented, InfoMax and Fast ICA. This is partly due to historical reasons, as those algorithms were used in the early EEG studies using ICA and have been used most frequently in the literature since then. InfoMax is probably the most used one and very often cited in publications. They go different but similar ways in finding the optimal ICA matrix. However, rather than going into the details of the algorithms now, I will come to this later again when we check the options in Analyzer. However, these two are not the only ICA methods available. Many more methods have been developed in the last 20 years, as you can see in this table from a Delorme paper. This table orders the algorithms depending on their mutual information reduction, which means how well they lead to independent components. From their position in the table, we can also see that InfoMax and Fast ICA are quite well performing. Though admittedly there is not a huge range from the best to the worst performing algorithm, generally speaking they are all doing quite a nice job. Now we're finished with the first part and learned a lot about ICA theory. Let me give you a quick summary of what we discussed. ICA can unmix a mixed signal that was recorded from multiple sensors. ICA is a purely statistical method, and we learned about its assumptions and methodological principles. The core principle of ICA is to maximize statistical independence between extracted source signals. However, this process can be reversed by inverting the ICA matrix to back-project components onto channels, whereby the inverse weights can be plotted as component topographies. This can be done completely or incompletely by removing selected components before back-projection. And now we come to our second part, which is applying ICA. In this part, we will check in Analyzer what are the available options and what they exactly mean, given that what we just learned in the theoretical part. Let's have a look first at the ICA procedure in Analyzer. First, the data has to be preprocessed properly. We will check the recommended preprocessing steps in a minute. Second, the actual ICA process, which involves unmixing the channel data, check the quality of the decomposition, and evaluate the components. This ICA procedure can be done in Analyzer using two different pipelines, and your final goals might be the decisive factor which pipeline to follow. If you rather plan to select only specific components and back-project them or analyze them even in component space, you would rather go for the transformation ICA and eventually combine it with inverse ICA. If you wish to use ICA for artifact rejection, especially for ocular artifacts, then you would maybe rather go for the transformation Ocular Correction ICA. Here you can see where those transformations are located in Analyzer ribbon menu, but we will see that in a little bit again when we move to Analyzer. Those two pipelines are different in a few aspects, but in general, the underlying ICA algorithms and options are identical. Of course, you can also select which pipeline to choose based on your individual preferences. There is no need to strictly follow this proposed segregation. So before applying ICA, we should talk about preprocessing of the data. Generally, you can calculate ICA in Analyzer on any sort of time domain data, may it be continuous or segmented. So you could even do it directly on your unprocessed raw data. But there are good reasons not to do this, since the quality of your ICA strongly depends on the quality of the input data. So you should do some balanced preprocessing, keeping enough high-quality data, but at the same time trying to fulfill the statistical assumptions of ICA. Usually two preprocessing steps are recommended: filtering and some artifact detection and removal. On top comes the selection of appropriate input data regarding the number of channels and length of the training interval for the ICA algorithm. Let's check those preprocessing steps in detail now. Using a high-pass filter is generally recommended to get rid of slow potentials that can massively deteriorate ICA. However, one has to consider the consequences of the filter settings for subsequent analysis. Let's say a cutoff of 1 Hz will definitely eliminate all slow drifts, which is good for ICA, but might not be ideal for finding ERPs later on. So in general, people try to use the high-pass filter in a balanced way by selecting a cutoff that is neither too low nor too high. You can, of course, always try out how well the decomposition looks like, and if it's not good, then adjust the filter and run at ICA again. There is some literature published that favors indeed to use a cutoff between 1 and 2 Hz, since this results in very clean decompositions, but then to continue later on less or unfiltered data. I will show you this very special pipeline later. On the other hand, a low-pass filter is not so critical for ICA, but if your data is strongly affected by high-frequency noise, you should better combine your high-pass with a low-pass. Why has there to be some artifact detection before ICA? This is for a simple but maybe not so obvious reason. We learned that ICA can decompose a signal mixture into independent components, and artifacts are very likely independent from EEG activity. So ICA should be able to separate them from the EEG data. This is true, but if you have a lot of non-stereotypical artifacts in your data, this might become a problem. Very stereotypical artifacts occur all the time, and in the end, all occasions of the artifact might fall onto a single component, and you can take that out if you want. However, non-stereotypical artifacts like EMG bursts or whole body movements do not occur regularly. So the danger is that every occasion of such an artifact is in the end unmixed to an individual component. And if that happens a lot, your maximum amount of components is reached very quickly. And there might be not enough components available to decompose the source signals that you are really interested in. Therefore, the recommendation is to mark the non-stereotypical artifacts that you are not interested in as bad intervals. And this could be done with either raw data inspection for continuous data or artifact rejection for segmented data. As you can see in the graphic, the areas in the data are marked as bad intervals, and they are neglected in the data matrix X when the unmixing matrix W is optimized. This means that those marked artifacts will not contribute to the weights that decompose the data. Lastly, an important implication from the story just told. Stereotypical artifacts that you might want to decompose, for example, eye blinks, should not be marked as bad intervals. Otherwise, they will not contribute to the unmixing matrix, which means that you will not be able to find a valid component for this artifact then, and you cannot remove it properly. Okay, now we will go to Analyzer in a short moment, and I just want to introduce the dataset to you that I will use for the practical part. Our example dataset is an auditory oddball with two different tone stimuli. There is an often occurring standard tone, of which there are 70 presentations, and a rare or deviant tone, of which we have only 30 presentations. The dataset was recorded with a 1000 Hz sampling rate, and it is only a little bit longer than, a little bit less longer than 4 minutes. So it's a very short dataset. The online reference was FCZ, and the dataset contains 32 channels. This includes already 4 EOG electrodes around the eyes and 2 mastoid electrodes. In order to focus right away on the ICA, I have already pre-processed the dataset, and you will recognize again the steps I've just mentioned. The data was first re-referenced to the mean of the mastoids, as this is the usual reference scheme for an oddball paradigm. Then the dataset was bandpass filtered between 0.1 and 40 Hz to remove slow drifts and high frequency noise. And finally, a raw data inspection was applied. And in fact, the dataset, you will see that in a minute, is very clean, so that I almost did not mark anything as bad intervals. So almost nothing will be included, while I used already rather conservative thresholds. Besides this dataset, I have also brought an additional dataset from another experiment where the visual evoked potential to a pictorial stimulus was investigated. This dataset is already completely analyzed with ICA, and I will just use the results of this dataset to show you more examples of independent components later on. Okay, let's now very quickly go to Analyzer for a short while, just to show the data to you. So here are my 2 data sets, and we will now start with the subject 1 oddball, and I will just right click and expand this. And as you can see, here are the pre-processing steps that I just mentioned. So the data was referenced to the mastoids, and then it was filtered. And I will just open the data set that is filtered and just skip through the data. And you can see that this data set is very clean after the filtering already, so there's not much in here of artifacts, and therefore when I marked the artifacts, almost nothing was marked. And importantly, as you can see, I have not marked blinks, as I might want to decompose them with ICA. Okay. So just before we work on this, let's very quickly go back to the slides for one more slide, because I have here already another sketch of the ICA process that we are going through now, and it's broken down into a couple more steps. So we already saw before the three main parts in our sketch: the computation of the ICA, the quality check, and the evaluation. And the computational part is again broken down into the sphering with PCA to apply the ICA unmixing, and the evaluation part again into examining and selecting the ICs and back projecting selected ICs. I will talk you through all of these steps, and then we will check the dialog and options of the ICA and inverse ICA transformations on the way. Okay, so let's go directly back to Analyzer, and I will close the filters node, so just that the raw data inspection node is open where I want to apply ICA. And for that, I go now to transformations, and the ICA and also the inverse ICA can be found in the frequency and component analysis group in the ribbon menu. And I open the ICA, and we will now go through every dialog page. So on the first dialog page, you are asked if you want to save the matrix files, so the ICA matrix and the inverse ICA matrix. You can decide how to name them. You can also decide where to save them. So the export directory would be the obvious choice. It is not in general necessary to save these files because they are also saved in the properties of the ICA node that I will apply here. And then if I later on use inverse ICA, it will just go up in the tree, find the matrices saved in the properties and use them. So you do not have to search to store the matrices on hard disk, and when you call inverse ICA to select them manually. Also, in case you do not save the matrices right away and you want later on still to retrieve them, we have also an ICA matrix export under the Export tab of Analyzer, where you can retrieve them post hoc from the ICA node. One more important thing here is if you want to save the matrix files for ICA and inverse ICA, add some clear name suffix, because otherwise they would write to the same file if you call them in the same way. And also use the placeholders, because then it will add the subject, one oddball name here of our history file. This is especially important if you run this process in a history template across subjects. Otherwise, the matrices will always be overwritten. I will actually disable this option now because, as I mentioned, it's not really necessary to do that, and so I will just save the disk storage. Let's go to the next page, and here I have to select the channels that I want to use for the ICA decomposition. So some channels are already selected here. As you know, Analyzer always reminds what you did last time, so I can now change my channel selection if I want, and it tells me down here what's the number of selected channels, and I will actually enable all of them, also my sculpt channels, but also my EOG channels, and I also have the two reference channels in here. I mentioned earlier, so the dataset is referenced to A1 and A2, the mastoids, and I mentioned earlier that it's good not to include them because that causes a linear dependency. However, I want to showcase to you what happens in that case, and that's why I will include them for now. The number of enabled channels is 33. That means the number of ICA components that we will get will also be 33. You can also decide a number of components, and also you can decide just to get components with a certain eigenvalue. However, these are very special use cases, and they will lead to non-square ICA matrices, which means these processes cannot really be inverted anymore. So if you back project the data, it will not end up in the same way as if you use the same number of channels and components. So we would usually not recommend using these two options unless you have very good reasons to do so. Okay, I will go to the next slide. And now here it's about deciding which data to use to compute the ICA matrix. I can use the whole data, or I can use just an interval of the data set. So the ICA matrix does not have to be computed from the whole data set. You can just compute it from a smaller but representative part of the data. So in this data set, first of all, it should be sufficiently long, so the data stretch that I use for training. And also it should feature everything that is representative for the data set on a whole, so that the unmixing weights that I get will also be able to decompose all what I want to decompose across the whole data set. You have also the possibility here to enter the start and end and length of the interval by yourself. You can also use this suggested values button here and then say, okay, I just want to use the default length for the 33 channels and I want to get that in the middle, and I just do that for now. And you see I end up with 21.78 seconds. So this is a very, very short stretch of time. And I would assume this might not necessarily be representative for my data set. So I would maybe not want to use that. So what I can do now, I can still stay in the middle, but I can beforehand also enter a longer time here. Let's say I want to use 200 seconds. And then I can also shift that like here. You see, it depends on how I shift that here, and the times will also adapt because there was just not a lot time left when I moved the bar here, so the 200 seconds couldn't be kept. So this is just make sure that you change it here, and then when you before click next, that there are really the values inside here that you want to use. You can also use some different options, equal intervals around markers, interval markers, or start and end markers, and use only the data in between to train your ICA. You can, of course, always use the whole data. I would actually do that in this case here because, as I said, our data set is very, very short. So it will not take too much time, but generally if your data set is quite long, let's say you have a recording of 30, 45 minutes or longer, the more data you put in, the longer it will take to get the ICA matrix. So you might want to reconsider taking just an interval and not the whole data. Okay, go to the, oops, sorry, that was my bad. I clicked too fast. So. Again, now we're here on the last page actually of the ICA dialog, the selection of the algorithms. So here we have the sphering and the ICA algorithms, and I will get back to that in a second. But before we do that, I want to explain to you the sphering. So let's start just with these options on top here, and then we go step by step through them. Okay, I go back to my slides for that. So we talked about the sphering before, and I mentioned that it is considered a necessary prerequisite for ICA because it actually leads to a better and a faster convergence. We actually do not need to go into details here because the sphering is also happening automatically in Analyzer, so you do not have to make a decision on the single steps of the sphering. But there are two options, as you just saw in the dialog. One is called classic sphering and one is called probabilistic sphering. Usually you would go with the classic sphering if you want to back project the components to channel space after you made a component selection. However, if your plan is to work with your data in component space after ICA without back projection, then probabilistic sphering is helpful as the resulting components are statistically denoised. Importantly though, when you use probabilistic sphering and back project your data, then this added noise will also be back projected to channel space. So this could artificially add noise to your data. So in most of the cases where you plan a back projection, go for the classic sphering. The last point here was also already mentioned. In case of linearly dependent or multicollinear data, the sphering will reduce your data rank. And I want to show you an analyzer what happens in this case, and this is why I included actually the reference channels in the data. So I will switch back to analyzer. And so I go with the classic PCA and I just leave the defaults as they are for the moment. And I just click finish now. And now comes this. So you saw the last step here in the bar beforehand was computer covariance matrix. So this is part still of the sphering. And now this pop-up comes and it tells me you want to compute a number of 33 ICA components because there's set as many components as channels. But the data has only rank 32. So this is due to the linear dependency because I added my reference, which consists of both the A1 and A2 channels. And now this channel is implicitly connected. So the combination of these channels is implicitly connected in all channels because as the reference, it's subtracted from every channel. And therefore, this channel is kind of redundant. And that's why the dimension of the data matrix is not really 32, but just 30, not really 33, but 32 instead. So there's one redundant channel in there. And the PCA that happens before ICA would now detect that and suggest to us to do something about that because this is not really valid. So if we actually say no now and we want to compute the 33 ICA components as we asked for, this redundancy will not be cleaned up, and we would not recommend to do this because this can happen or it can result in an invalid ICA decomposition. Instead, you can click yes, and then the number of the 33 components will be reduced to 32, so this linear dependency will be cleaned up. You can also press cancel, and I will actually do that because the third thing I can do is just that I reopen my ICA, and I will just not get to this point by excluding my reference. So I disable my A1 and A2 channels, and now only the scalp channels and the EOG channels are in there. Of course, this results now in only 31 channels that I enabled, and I will only get 31 components. And then I click next again, and I leave again the interval for the training. You saw already in the first attempt that the whole data led to a very, very quick decomposition here. Okay, and now back to the algorithm page because I still want to talk to you about the other algorithmic options. And I go back to the slides for that for a second. Okay, first of all, you need to select here between Infomax and Fast ICA and restricted and extended. And obviously that leaves us with 4 potential algorithmic options because I can combine them. So Infomax and Fast ICA, we heard already about them. There are 2 different measures to calculate the ICA, and they're using 2 different measures to assess independence. Fast ICA, as the name suggests, is meant to converge faster than Infomax. And in fact, Fast ICA is an optimization of the Infomax algorithm. But they are also different in the sense how they evaluate the components. Infomax uses a non-deterministic algorithm and can thus deliver slightly different results when you run ICA again on the same data set. Or let's say you run it on the same data set on 2 computers. So it might be very similar, but it is not 100% the same probably. Fast ICA, however, is deterministic because it uses a fixed point iteration, and every run will deliver the same results. Different is also the number of steps, 512 versus 150. The maximum value, of course, only takes effect if the algorithm does not converge beforehand. And since fast ICA is supposed to run faster under ideal circumstances, a smaller number of maximum steps seems also reasonable. However, fast ICA may actually not run faster if it has to struggle with a lot of weak components, which are almost Gaussian in their distribution. And in fact, those occur quite often in EEG data. Now to the main difference between restricted and extended. The restrictive versions of the algorithms use the same training method for every component and convergence step, while the extended version adapts the training method in every convergence step to the kurtosis of the currently extracted component. So this might sound a little bit difficult. The quintessence is the extensive algorithm is an adaptive algorithm, and this means it might actually be more effective in the end, but it will take longer than the restrictive version. One important point about the restricted Infomax algorithm, which we used actually in the last run that we did, it can only separate components with positive kurtoses. So unlike the extended Infomax, which can also extract both positive and negative kurtoses. So keep this in mind when you want to decompose your data in order to remove line noise, because we learned beforehand this has a negative kurtosis. So that would not work properly with the restricted Infomax. The last option is here the biased option, which you can combine with the Infomax options, not with the fast ICA ones. This alters the method in a way that components with a positive kurtosis are preferred. Okay, and now we're going back to Analyzer again. And we will actually run ICA now. There is some more options down here. One of them is the ordering. This has no effect on the calculation of the ICA. This will just have an effect on in what sequence the components will be shown in the result. So which is the first, which is the second, and so on. So they can be ordered based on kurtosis or their energy value. The convergence bound is the number that has to be met when the ICA matrix is optimized. So I need to get under this number with the last iteration step. So in every iteration step, I try to approach this number of the convergence bound. And once I'm under this number, then I have reached my W max. So then I have reached my criterion for the independence that I want to achieve. And if in a certain number of steps, because I have to define a number of steps, otherwise it could happen that ICA runs for eternity if it's like caught up in a local maximum or something, then it can happen that it will stop by itself. And this number of steps is defined here as 512. So these two numbers, they are well defined in the literature by the people who have brought up these algorithms. So I would not change these in fact. And lastly, down here is the semi-automatic mode. So if I click that and I finish, then my ICA calculation will run through and I will get directly into an interactive ICA window where I can examine the data and I can also back project. And if I do not click that, that is not a bad thing. And I want actually to show you why. So I will not click it. And again, so I have used the options that we just discussed. So classic PCA, because I might want to do a back projection, and the Infomax restricted, which is probably the most often used ICA algorithm. And I click finish. And again, this will run through, and I would not expect now a rank warning, and there is none actually. So this should again go rather fast as the data set is very short. And you can see now here it says it started 10 times and it's at a certain convergence rate now. So it tries, you have maybe seen that this number changed a little bit in the beginning. So it goes down very quickly and then it approaches really this convergence bound. And once it falls under it, then ICA should stop. This takes a little longer this time. But let's not give up yet. It might actually be finished in a second. So this might take a little longer this time because I changed some options as compared to the first run, or it might just be because my computer is rather slow. So there we go. So you have to keep a couple of thoughts in mind. So of course, the faster the computer is, the faster it might run. The more data you put in, the slower it might run. So that goes for the number of channels you put in, but also for the number of data points that you put in, sorry. And actually, I think I did something wrong, because you can see now here that I did not something wrong. Sorry, now I confused myself. So because I actually did not put in, I increase the number of channels, because I actually did not put in my reference channels, you see A1 and A2 down here. So they're not thrown away, but they still appear as normal data channels. So you have here now the peculiar thing in this view, that you get components, and you see they start with F, and then they are numbered from 00 up to 30 here. And then I get like real EEG channels below, which are my references. Okay. So now I have this ICA node here with the channel, not the channel data, but my components. And you see I can also now navigate through this data. I also still see my bed intervals, but the data looks clearly different from what I had before. So I did not use the semi-automatic mode now, which means I get this node ICA. If I would have used the semi-automatic mode, I would also get a node ICA in the end, but in this node also the evaluation and back projection step might already be included. However, I can also run ICA like this, and I get this node, and then I can just open the interactive window by clicking the inverse ICA transformation, which you just find below ICA. And then you get this pop-up semi-automatic mode. You just say OK, and then this opens up. So otherwise, this would have opened up right away in the same node. The difference might sometimes become handy, because if you say, okay, I actually have a lot of data and I want to run ICA for all of them sequentially overnight maybe, so that I come back in the next morning and all my ICAs are computed and then I start evaluating them, then you might actually not want to use the semi-automatic mode in ICA, because then it will just run through, create all your ICA nodes, and you just go into them with the inverse ICA. If you use the semi-automatic mode right away, already in the first computation, this interactive window would pop up and it would just not run further, because now it wants you to give manual input. Okay, so if you remember beforehand, I said there is actually the calculation of the ICA, and this is the evaluation here. So there is a step missing, which is the quality control. And even though I'm already here in the inverse ICA, I can still go to the ICA node, and I can right-click and go to the operation infos, because the operation infos give me an idea about the quality of the data set. So it tells me again what I put into here, what algorithms I use, which channels are in. Then it tells me also how long the data is and how much data it used. And this is interesting now, because the data has roughly 231 seconds, but 226 seconds were used. So I used the whole data option, But since I have bad intervals in my data, these are subtracted from the length. So that's why it's a little bit less. It's 5 seconds less. So now it tells me it converged in 96 steps after 9 restarts. So you remember maybe when we were waiting for the ICA to finish, it was in step 10. So actually it converged in this 10th step, and that means it started 9 times beforehand already, and this is documented here. And 96 steps was the time when it converged. This is very important because we know that the maximum is 512, which means we are very far away from this maximum. So first of all, it says here that it is converged and then in this number of steps, and I would be happy about this. So I would assume this should be a valid decomposition because it converged in a number of steps that is far away from a maximum. And also the second number, there is not really, so for both numbers actually, there is not really a hard criterion when this would not be good. So usually if this number of the restarts is maybe around 10 plus minus, I don't know, 2, 3, 4, this should usually be fine. If it goes around 20 and above, then maybe there was something wrong, but then also this number might go up and actually the data might not converge. So in case that the 512 steps ran through and it didn't converge, it will say so here that it did not reach convergence and stopped. And then it tells us here that at the last step, so at this 96th step, it reached a certain value, which is a value that falls below the convergence bound, and that's why it stopped. Okay, now here you can actually see our components, and they tell us this kurtosis and energy values. And again, these were the these were the ordering factors that I could select. So I selected energy, which means my F00 component is first. If I would have selected kurtosis, you see the ordering would have been a little bit different. But anyway, as we will see in a second, it makes a lot of sense to look at all these components and not just at the first one or the first 3 ones. So the ordering does not matter that much. Okay, so I click OK again, and I would assume that this quality achieved here is fine. So now I am in the Inverse ICA overview, and I want to check with you what we see here first. So this looks already a little bit messy, and this is because we see here now the components, and it will scale down a little bit the amplitude, and you see below here is our real channel, and this has a much lower amplitude. So the relation from component to the real EEG channels and amplitude is quite different. And this is because the components come up in arbitrary amplitude values, so they are not scaled. So first of all, we have the time courses here, and we can skip through the time courses, as we know. And make sure to check always in the beginning, like I said already, what is shown here. So we have the components starting with an F, and then if you have any channels like I do here now that you did not include in the ICA, they will come on the bottom afterwards. So the A2 is actually then on the next page. Okay, so then up here, what do we have here? I will make that a little bit larger. This is the weights. So the weights that we extracted with our ICA matrix, and they are shown here for every component and every channel. So you can look for every component channel combination for the weights. And this can sometimes be quite interesting because if the weights are very large, for some reason, you might get a hint for a certain component having to do more with that specific channel than with others. We will actually see that later in the Ocular Correction ICA, where this looks a little bit different, but then it might make more sense. Okay. The column here in the front with the hashtag symbols is very important because this can be used to remove an ICA component. So it's green, which means if I back project now, and actually if I click finish here now, the data will be inverted and back projected. So if nothing here is red, and at the moment everything is green, the data that I get back will be the same as the data before ICA. However, if I now double click here, it will turn red. And this means now that I selected this component for removal, and if I click finish, it will be not in the data anymore. So then my data will be different from the data before ICA. Okay. Below the weights, we have a topography, and the topography shown here is the one of the component that I have clicked here. So if I click through them, it will change. And remember, we have only one topography per component. So this is has nothing to do with the time window I'm looking here at, but this is for the whole time. And as usual, you can customize the view here by right-clicking and going into the settings. So you cannot change it to a different view like the 3D mapping view. It has to be the 2D mapping view, but I can also say, okay, I rather want to see the front or the back. You can also change the color scales and the scaling. So it's the usual options that you have to customize your plots. Below the topography, you have a couple of options, and I will start actually with this here, the drop down, that is the modes. So at the moment we are in ICA component mode. That's why we see the ICA components here. I can switch to correction, and this will actually show me how the data will look like after I finished and back projected the data. And so this should at the moment look exactly like before because I didn't remove anything. However, the nice thing here is, I increase a little bit the amplitude. If I now remove something like this first component, you see there is something changing. It's not much. I maybe take the next one. Oh, and there you see a lot is changing because this component seems to be related to our blinks that we see here. So you can test right away what happens if you remove a certain component. And the nice thing is that in this mode, you can also do overlay with complete data. And if I click that, it will overlay with a red curve. And this is actually the complete data before ICA. You don't see a difference now, but if I remove now here, then you can see what happens, what was the data beforehand, and what is the data after I removed it. And you can then skip through the data and really check thoroughly what this component is, what it will happen if you will remove it. So this is very handy for evaluating the components. A similar thing is, I just unticked that shortly, if you go to the next mode, which is the subtracted mode. So this shows everything and summed up across all components that you remove. At the moment, it's just flat lines because nothing is ticked to remove. And if I double click again, it will show me the effect, what will be removed from the data. So you see here again the blinks. So this is again very nice if you do that for a single component to see what is this component actually doing in the data. What's the effect of the component? You can see this and also the correction before projects back to the channel data. Be careful though if you use this mode, because if you untick more than one, so I check all one, that and that, and you see it changes. So this shows you always the summed up effect of all removed components. So it really depends on what you want to looking for. So if you have selected a couple more and you want to see what's the combined effect of removing them, then fine. But if you really want to see what's the individual effect of one component, then rather go for that. However, you can of course also check at the component time course in the ICA component right away. So you can also, as usual in this view, just click and double click maybe then on this component, and you then just see this one component, and you can also check the time course of that component on its own. I double click again to go to all. So there is a fourth mode again, which is called topographies. And this will show us all topographies so that I do not have to skip through them. So I see them all next to each other. However, here is the problem. I only have one common scale, but my components have very strongly differing amplitude values, again, because the amplitude values are rather arbitrary. So what you can do here is use this show node mappings option, and that will rescale them. So you see directly that down here, the scale changes. So this rescales them, and then you can rather compare them against each other. Okay. Then let's now go back to the ICA component view. And so again, I will take out one component here as an example, and I will take this first one, the F00, which was the one with the most energy that was removed. So what is now a nice thing to do, because we would always recommend not just to look at the component topography or not just looking at the weights or the time course, but check everything together. So you can just take this out and skip through this and really look what happens. And then if you come, for example, to this point here and you want to see, okay, what is this? This looks huge here. What does this actually do in my data? You can do something very nice. You can mark that here also. You can open a transient view, but I don't do this. And then you go maybe to correction. And then you can see, so nothing is taken out. The marking is still over the same time. And you can actually see here what's happening. So the only thing that you see here that is rather a big deflection is down here in the ocular channel. So this might have to do with that. So by switching back and forth between component and correction, you can quite nicely see what's the effect of a certain component. And as I told you, you can now also go to the subtracted, and you can remove this component, and then you see, okay, that really has to do with these ocular channels and also here. So this seems to be part of our ocular artifact. However, you can then also check through all channels and through the whole data set and really look here, go back again, what's the effect of this, and really to see, is this only having an effect on the ocular channels? Because what you want to do here when you evaluate the components is you want to be sure what a component is, what it does, where it comes from, and then maybe decide to remove it from the data. And of course, this bears the risk to remove something that is actually real brain activity that might be correlated with your task. And if you remove that, you might, you will take that out of the data after back projection. And that means that you might diminish the effect sizes of your actual effect of interest. So you have to be careful what you take out, which is why we would always also recommend to check every component in detail. So this takes a while, of course, but it is really worth looking at all these topographies. So I will skip now here through the topographies and also the time courses. But you see a lot of these topographies, they do look like, okay, there's happening something somewhere, but there are some topographies to look for that might help you already. Okay, this is maybe a component I have to check in detail. So this one here, for example, looks like it's really just happening at this one electrode, while this one here looks like, okay, there's a lot of stuff involved here. And so this can give you already a hint what's going on with this component and if it might be sensible to take it out or not. There are also some very classical components. So you saw already this one seemed to be very much connected to the blinks. That one also had something to do with ocular defect, it seems. And you can see they are quite similar, just inverted. And also, if I show you this here from not one map, but from the front, you can also see this. So this is, for example, a classical topography to look for ocular artifacts. However, I will show you later again some more examples of that. Okay, so what do I do now? So just as an example, I will remove now my first component from the data. So I double click and I see in the subtracted something happens. And now I will actually click finish. And what I get now is my inverse ICA node. And what I can do now again is that I just overlay, not with the ICA node, that will not work, at least not for these channels. That only works for the channels that were also in here, because the other channels were not in this node, but instead they were the components. So in case I want to check what happened from here when I took out now component FOO, FOO, and I want to see the effect, I overlay the node before ICA. And then I can skip through the data and see what's the difference. And this might again help you to decide if this was really the right thing to do, because the nice thing is, of course, that you can easily now add a second inverse ICA node, or you can also reopen this one here with the added parameters reprocess, and you can make a different selection if you think, okay, this was not the right thing what I just did. I believe I took something out that should stay in the data. So the way Analyzer operates with its branched structure here enables you to just make several selections and then also compare your selections against each other. Okay, so I want to show you one more thing here with the ICA node, because now that we have a node here containing the components, we can actually also work with them, because these are time domain signals like the channel data, and we can actually apply transformations to them. Of course, as I said, it doesn't necessarily make sense to apply all kinds of transformations here, because this is not proper EEG data, but just the components with arbitrary units and amplitudes. But some things might make sense. So, for example, you want maybe to further check the components to be sure what they are, what they have to do with your EEG data. So let's say you maybe do not want to find a component for your blinks, but you rather want to find a component for an ERP component. So what you can do here is you can apply, for example, a segmentation and segment the components in the same way you would segment your ERP data. So let's do that as an example. So I go to segmentation and I use the segments based on the marker position because I have markers. And I will just take out the deviant stimuli. So I have 30 deviant stimuli, and then click next. And I use here -200 to 800, so segments of 1 second length. So this would be what I would do maybe if I analyze the time domain signals, so the channel data for my P300 ERP that I would investigate in the oddball data set. And if I finish, I now get these segments that still are not channels but contain my component data. And you can skip again through them, and also you can average that. And now you have the average of your components, and you can look in these, for example, if you find something that looks similar to your P300. And then maybe, because there are some papers, for example, that say, okay, we want to use ICA for reduction of our data set. So we just use the ICA components that we bring together with some ERP process that we want to look at, and we forget about everything else. Another thing you can do here is, and this is something that those of you who also have worked with EEG Lab might know, you can get a so-called trial image. And this is sometimes quite nice to evaluate a component. So you have now the average here, but you can go back to the segmentation and get a trial image. And this is something that we have available as a solution in Analyzer. And this is called the stacked plot. If you do not have that in your Analyzer, you can download this from our website. I click the stacked plot, and this will create this solutions image here, this trial image here. And now I get something that looks like a time frequency plot and is actually misusing this in Analyzer. And if I now double click on my FOO component, I do not get a map down here because I don't have components. But now I can see what's the effect of this component across trials. Okay, in the same way, you can also, for example, look at the frequency spectrum of your components and then also take that into consideration when deciding about channels, removing components. So as I mentioned, I have also another data set here, which is this visually evoked potential data set, and I expand it now. I close everything else. And as I mentioned, I have already analyzed this completely. And you can see here that I did something the same thing. And in this ICA node, I double click now and I will actually open, hopla. Sorry, I will actually open the Inverse ICA. And here again, I can also check my components. And as I mentioned, I wanted just to show you some examples for other components here. So actually, this is done on segments. So I see only a segment here because ICA can also be computed on segmented data. And in here, so in the visually evoked potential, I found a component, and this was component number 19, that looks very much like it might show our visually evoked potential, because I averaged this component. And if you look into it here, so component number 19, then here very early you see big deflections. So in the time range where you would also expect your visually evoked component. And if I look in the stacked plot that I just showed you and I check for component number 19, you can also see here that this seems to be something, you see these red and blue bars here, that goes through all trials. So this is quite a nice way of finding such a component that might reflect some EEG activity. Okay, another thing that I found in here is a nice component, that was the FO2, that reflects a pulse artifact. And if you look in component number 2, I marked it here, and you skip through the channels, here you might see it nicely. You see that there are somewhat regular spikes in here. And so this is a typical topography around the edges, and you have this dipolar shape for a pulse artifact. And so if I take this out now here, and I go through the correction first, so here you see it also in the data, you see that there is definitely some pulse in here. And if I now double click, this will be taken out. So as you can see, ICA can decompose all kinds of artifacts, and you can also get rid of these artifacts. And in the last part now of our webinar, I want to talk about another artifact that you probably want to use with, want to get rid with ICA the most. And this is, of course, our ocular artifact. So for that, I actually, as you have seen before, I had my ocular artifacts like the blink component also here in my ICA. So you can, of course, use ICA for this, but in the last couple of minutes in the webinar, I will actually show you how to use Ocular Correction ICA for that and also showcase the differences. So I will close this data set here again. Let me go quickly back to my slides. And actually, let me first give you a brief summary of this part so far. So in this first practical part, we learned that unprocessed EEG data might not be ideal for ICAs, so filtering and artifact detection are recommended. But be careful, do not mark the artifacts that you want to decompose. After running ICA, you should check the operation infos and see if the algorithm converged. ICA will not label your components as you saw, so the interpretation and decision what the component is up to you. And use the available visualization tools that I just showed you to base your decision. And if you want to work in component space or channel space after back projection is up to you. Okay. Before going to the ocular artifacts, I already mentioned at the beginning, there's one very special pipeline you might be interested in. We receive sometimes customer requests where people ask explicitly about it because it's mentioned in a couple of papers. And I will in one slide very briefly go through that. So I talked about this when we talked about the filtering. And in this special use case, people want to compute ICA on data that is more strongly filtered than you would require for your actual analysis. However, people do that to get a cleaner decomposition. And then you would take the weights from this highly filtered data where you applied ICA, and you would apply these weights to differently or even unfiltered data. And for this approach, you need to deviate from the standard pipeline that I just showed to you. And in the first dialog page of the ICA, you need to save for this pipeline the ICA matrices. So you need them as external files for this. And you can do that, as I mentioned, on the first page right away, or you can use the ICA matrix export later on. This graphical illustration from a paper by Winkler demonstrates the logic of this special use case. But the important part is actually just here in this box for us. The data is high-pass filtered, for example, between 1 and 2 Hertz, and then you get rid of all slow potentials, and the algorithm is then trained on this data, and you receive your weights, so your unmixing matrix W. This unmixing matrix can then be applied to the raw and unfiltered data, and the authors call this an IC filter. And this procedure can be mimicked in Analyzer. However, you need to apply the ICA unmixing matrix that you stored as a file via the transformation linear derivation. You will apply this then to the unfiltered or to the less filtered node, so maybe just with 0.1 Hertz or so. So I have also down here a sketch of how a tree might look possibly. So you have the high filtered data, the ICA to get the weights, then you go to lower or differently filtered data, and then you apply the weights with linear derivation. So this will transform channels to components and unmix the data. If you then want to back project again the data, you have to apply linear derivation again, and then you apply the inverse ICA weight matrix that you have also to save before. And this will then transform components back to channels, so this is our back projection. And however, if you want to remove a channel in this case, a component, sorry, you will have, after you loaded the inverse matrix in linear derivation, to zero a component. So you have to do that manually. So all the weights of one component that project to all channels, you would just add zeros in this column of that component across all channels. And this will remove the influence of the channel. So this is a little bit more abstract. In case that you need for information for this approach, if you want to do this, you can just drop us an email to our support account. Okay, now let's come to the practical for our second part. This will be a rather short one. but I still want to show you Ocular Correction ICA, as this is probably for most of you the main use case of using ICA to your EEG data. This is a specialized version of the general ICA transformation, which identifies and pre-selects components with time courses that are potentially associated with eye movements and blinks. So if your goal is to use ICA just to remove ocular activity from your EEG data, you can follow this pipeline here. Everything what we learned about the algorithmic options stays the same though. Some additional steps come on top, which will make your lives easier when you look for EOG artifact components. But don't get me wrong, ocular correction may be designed to help with ocular components, but as I said before, you can use also this, like the other ICA transformation, to get rid of other stuff, or so in the end, both ICA transformations that we have are fully fledged ICA transformations. They do the same thing. You can just do a little bit on top with this one. However, this one is also missing some options that the other one has. Okay, just to give you a little bit of information again of the ocular artifact that we want to remove with ICA, let's recap that quickly. So the human eye forms an electrical dipole, and since we're moving our eyes all the time, the electrical field of this ocular dipole is changing dynamically. Due to principles of volume conduction, those electrical artifacts spread throughout all layers of cortex, skull and tissue, and they are present at any scalp site, though their strength decreases with distance from the eyes. Ocular artifacts have a much bigger voltage range and thus interfere with the detection and analysis of cortical responses of interest. And there are two main components of the ocular artifact, a vertical and a horizontal component, and you can see them here on the right. The vertical or VEOG activity is characterized by bell-shaped deflections and has this rather central, also bell-shaped structure here in the topography. And the horizontal activity is rather boxcar shaped and has this rather dipolar topography, whereby it doesn't matter, as you remember, the polarity of these topographies is arbitrary. So it could also be that you see here the negative colors and here the positive colors and here also the other way around. Okay, so let's now check our ICA. Ocular Correction ICA, and I will apply that to the same data node where I applied the ICA. So I open again my raw data inspection node, and the Ocular Correction ICA can be found here in the artifact rejection reduction group. Okay, so the first thing to check here is some more general options, because there is a blink marker detection in the beginning of ICA, and I can either create new markers or I can use existing markers. I don't have any markers at the moment here for blinks, so I will create new markers. You can only place markers with this transform as well, but actually I also want to do an ICA based correction. And then you have the same here, the semi-automatic or automatic mode. And here we would always recommend going for the semi-automatic mode, because in automatic mode, analyzer will decide what looks like ocular artifacts and remove them without you being able to assess them. So go for the semi-automatic mode. With the marker output, that is not really important. Either you want interval markers or pairs of start and end markers. So this is just about the blink markers. On the next page, you have to select the algorithm for the blink detection. And so just very briefly, I have a slide about that. So the first add-on is this that we did not see in ICA transformation. So we need to select VEOG or HEOG channels as well if we want to benefit from the detection algorithm that pre-select EOG components for us. And so these channels, first of all, they do not have to be EOG channels. So there can be some channels on the scalp that pick up the artifact. So if you are familiar with our other ocular correction analyzer, the regression-based one, there we would always recommend to use proper EOG channels. However, with ICA, this is not as important. So take a channel on the scalp if you want that picks up the artifact rather well. FP1, for example, picks up blinks very nicely. However, if you have EOG channels, and we have them in this data set, you can of course also use them. Then, as we saw in the dialog already, there are two algorithms available for the blink detection. One is the mean slope algorithm, which will detect the blinks based on amplitude activity in the VEOG channels or HEOG channels. And then we have also the value trigger algorithm, which works based on a template of a prototypical blink. Usually both of them work nicely, and we would just recommend to check what works better for your data. Okay, I go back, and so I will actually go now with the mean slope algorithm. These additional parameters down here you only have to enter for the value trigger algorithm, and they are of course explained in our user manual. Okay, on the next page comes now selection of the VEOG and HEOG channels. We just went through that. So I have here my my ocular channels, so I can use them. So I can use VEOG U, which is the upper one, and VEOG L, the lower one, so above and below the eye. And for HEOG, the left and the right one. And it does not matter if I do it this way or the other way around, and here the same, so that is arbitrary. If you just use one channel, so let's say you use scalp channels and you want to use FP1 for the VEOG channel, then you can enter the FP1 here. And then you do not have, of course, a channel below the eye, so you leave this box empty and rather use common reference option. Okay. Then we go to the next page, and again we have to select here our channels for ICA. So this is the same as in the other transformation. I will again use my ocular channels, and this time I will leave out the reference channels right away. And then again I can select which data to use, and again I will use the whole data because that worked rather fast. And I will also use again Infomax restricted, which is usually a good choice if you want just to remove blinks from the data. You see again here the options for the convergence bound and ICA steps. I would leave them untouched. You can also again use an interval and select which interval to use. And also we have this around blinks options. This option will just use the data around the blink markers. And I would only use this if you're really interested in getting rid of a blink component, but not if you're interested also in check any other components. You can also use this bound number of blinks. This means if 60 blinks were found, for example, so if I have that here, then it will stop searching for them. Otherwise, it will just search for all of them. So I will do it like this, and I go to next. And so this is again something added here, because this is now how should be ocular components identified. Because what this transformation does is it pre-identifies components for you, so that you get already some information what might be a blink and what might be a horizontal eye movement component. And let me quickly explain this to you on the slides. So the first one, the first method that we have checks for the blink intervals how much a component contributes to the global field power. The second one will examine the shared variance between components and the VEOG and HEOG channels. Please note for this method you can only use that if you have included the channels you selected for VEOG and HEOG also in the ICA selection. And the last one is based on correlation between component activation and VOG and HGOG activity. So generally, these will all check a component with respect to the channels that you have selected for VOG and HGOG. Then for all these methods, the components will be ranked according to their score that was calculated with respect to the selected measure. And afterwards, component scores are compared to the threshold, and this threshold is specified in the field in the dialog. So it's called total value to delete. And so it will check across the components how big their scores are and take, well, not take them out, but pre-mark as many components until you have reached this total value to delete that you entered. So depending on this, one or more components will be pre-selected as ocular and will already be marked as red in the semi-interactive view of the transformation. This threshold might though need some adaptation, so this is rather arbitrary what you enter here. And the thing is, if you have a lot of rather weak components, a lot of them might be pre-marked. While if you have a very strong component, maybe just one will be marked. So in any case, we would still say use your expert eye and visually inspect the data. So do not trust 100% just to this algorithm, which is why we also say do not use the automatic option. So check if the algorithm has worked, if a good job was done, but still verify if the components selected look really like they are ocular components, and also check the non-selected components if maybe something was overlooked. Okay. Then let's now go back to Analyzer. So I will just use the default values here. So this is the sum of squared correlations in both cases. And I just also go with the 30% here now. And on the last side here of the dialog, again, I can save my ICA matrix files. And I will not do this because, again, I don't need this in this case. So I click Finish. And again, it will run. And this will, again, take a little bit of time and is dependent on how long your data is. So, but since we have selected a semi-automatic mode now, what will happen is that we create now an Ocular Correction ICA node here that already opens with the interactive view. Which means we do not get this ICA components in a single node and then apply another node onto this. So this will be in one go, which means also for Ocular Correction ICA that you have, if you recompute it, so if you want to reconsider what components you took out, you have to recompute it with the ICA, because this is bound in one process here. While in this case, you can always compute the ICAs independently and then make the inverse ICA and reconsider what selection you have made. Okay, so I hope that the ICA computation will be done in a moment. But I guess it should actually take a similar time than previously, because as I mentioned, we use the same algorithms and also the same training data. But in this case, so it's actually a rather small data set, but in this case, actually my computer might also just be a little slow and need some more time to compute it. But I'm sure it will be computed in a second. And here we go. Okay, and now we're directly in the interactive view in the Ocular Correction ICA node. And you can see here now, so you see something here that is different, which is the blinks that were selected. So it looks like it captured all the blinks pretty much. You see here now the components already. And what is very different, you see here that now something is already pre-marked. And you don't see the channels here, but you see VOG and HEOG, because this brings now that together with the channels that you selected as ocular channels. And what you can do now is you can, for example, sort this table here for VOG and then check those components. And here you see already this looks very much like the prototypical topography we looked at. However, there are 3 other components marked here, and as you can see, so 30 was the number we entered in ICA dialog for the correlation with the ocular channels, and so this component only has a score of 22. And only when you add these 3 others, or maybe could also be less because this is marked for both of them together, but you have to add more to reach the 30. And this is why more is marked in here. And the same is here with the HEOG. So there's the first one, which looks very prototypical for our HEOG activity. However, it's just a score of 21, so something has to be added. So we should now check all the components that are marked as well, so not just FO1 and FO2, and I go back here in ICA to reorder them. So these here, I would say that looks very clear that they are ocular artifacts, and if we check them in the data, so we check them here first in the components, and you can see actually that the components show the boxcar shape and the bell shapes. And if I go for the correction, well, you can see now that there are no blinks in here because this has been removed. So if I overlay with the original data though and navigate to where blinks are, like here, you can see that they are actually gone. Okay, so but let's now check the other components that were marked. So this one really doesn't look like the topography that we are looking for, and we can also check that. So that's the FO4. And this one looks rather like something that this one electrode only happens. So that's the FO6, and then is also marked the FO8 and the F24. So from the topographies, I would say they all do not look like they have anything to do with ocular artifacts. And if we check through them, we also see actually that there is nothing in here that looks like blink. So this one looks maybe like there's something like yeah, it looks a little bit like a pulse, but it doesn't really have the topography, so it could be a technical artifact. So in fact, I would not select any of these. And for the sake of just showcasing what happens if we take out clear ocular channels, I will just mark these 2 where I'm really sure from the topography and also from the time course we saw. And now I can also go to subtracted and see what is really taken out by these 2, and I can quite surely say, I go from the front again, this seems to be only because you see also that a lot happens in the ocular channels, but also here you see everything happens in the frontal channels, and it's really taking out what I want to get rid of. So if I click finish now, the back projection happens, and again it happens directly in that node. So now I see here my data back projected. Where my blink markers are, I don't see blinks anymore. And I can again overlay that with the data beforehand and see the difference. Okay, that's it now for the practical part. So let's now summarize quickly. So we have, besides the classical ICA, an additional Ocular Correction ICA, an analyzer that has some powerful add-ons if you want to use ICA for EOG artifact cleaning. There will be a pre-selection of EOG components based on detection algorithms. However, as in the normal ICA, the decision is in the end yours and it needs to be decided responsibly. Especially the possibility that an EOG component might also contain real EEG activity needs to be ruled out by careful assessment. So it's still a subjective decision, but you can support it by using the help of the detection algorithms. Compared to the regression-based method, we would say you can also use Ocular Correction ICA nicely if you do not have the EOG and HEOG electrodes that you have around the eyes. This usually works well with scalp channels and is not so much dependent on these other channels. Okay, so as I mentioned in the beginning, we are not in a live session here, so there are no live questions. But we compiled a list with some questions that came up in the live webinars that we did on this topic 2 years ago. And a couple of them were quite interesting, so I still want to go through them for you so that you do not miss out on this information. The first one was, if marking artifacts as bad intervals avoids that they contribute to the ICA matrix, why does the data within the bad intervals look different after back projection? And this is something that is very clear actually in the data. So I have here my ocular correction node overlaid with the node before. And let's navigate here to my bad interval. And you can see in the bad interval, actually the correction takes place. The reason for this is that we use only the data without bad intervals for creating our ICA weight matrix. This ICA weight matrix, again, has a weight per channel per component. So time does not play a role in here. And also the data points and thereby the bad intervals do not play a role in this matrix once it's computed. And if we back project the data, we multiply this matrix with all data points in there, and we do not take out the data points in the bad intervals actually. So this matrix is still multiplied with all data points. And that's why you see also deviation in here. The nice thing is, the data in the bad intervals might have been cleaned by ICA now actually here. So I could actually remove the bad interval now and then I get more data. So I would always recommend to check if the bad intervals still are over bad data, or if ICA maybe really cleaned the data, even though there was an artifact that was not used for the matrix computation. The second question that we have in our list is, I have several experimental blocks which all should contribute to the ICA. So I use the whole data option, but then the decomposition takes very long. Is there a better way to do this? There is a nice way to do this actually, because it's a very good point to use data from every block maybe, because you want to make sure that the composition might not be biased to a certain block of the data, especially if the experiment is very long, or let's say it's 2 different conditions in the blocks and the ICA solution should not just be biased into one condition. So what you can do in this case, and I just open ICA dialog for this, here, where it is about selecting the training interval, you can actually, instead of just defining one interval, you can also use these options: equal intervals around markers and interval markers and start and end markers. So you can basically place markers in your data before ICA that define certain structures, for example, in every block of this experiment. So let's say 2 seconds, sorry, it's a bit short, 200 seconds maybe in every block if the blocks are very long, or if the blocks are short, maybe just 50 or 100 seconds. And then you put markers in the data that, for example, is start and end around these intervals, or just one marker of that length. And then you select this option here, and then the training data will be taken from all blocks from within these marked areas. So that's a way of getting this solution done. The third question is a similar one. It's if I have more blocks and pauses between them, do I have to remove these pauses as they have artifacts not associated to the experiment? Yes, I would do that. You could either do the same what I just explained. However, often there might maybe be just one pause or two or three. So what you can simply do is put a bed interval over these pauses. And this goes quite nicely if you, for example, just zoom out of the data. So you go into raw data inspection, and then you zoom out, and then you might see right away where the pause is, and then you just drag and drop a bed interval over the pause. Okay, the fourth question that I compiled is, does the inverse ICA transformation have the same effects as the ICA back transform option under solutions? This is usually how I do my back projection after specifying the components to exclude. I have selected this question because meanwhile we have changed our set of official solutions from our website, and actually this solution is not in here anymore. But of course it might still be that a lot of you have this and have used this regularly. You can still use this. However, we would actually encourage you to use the inverse ICA instead because it's just more stable. The solution is very old and a bit outdated and no further maintained, so it sometimes runs into errors. However, to answer the question, basically it does the same thing. So the solution is the predecessor of our inverse ICA transformation. And the only difference you might realize if you use them is that the solution is not adding back the offsets that it subtracts from the components. So it kind of removes also the offsets from the data. Okay. Let's maybe go for two more questions. They are short ones. Is it better to use continuous data or epoch data for an accurate ICA? Basically, it doesn't matter. So in my examples here, I use once continuous data and once epoch data. The important thing is that if you use epoch data, that the epochs contain what you need. So if you want to remove blinks and in your epoch data there are only 3 blinks, then you might not be able to run ICA properly on that. In that case, I would maybe rather remove these epochs that contain the blinks. But generally, it doesn't matter. ICA doesn't care about continuous or epoch data. And the last question for today, I only have a short test paradigm. Can I simply use a very high sampling rate to increase the number of points for better ICA results? As this question sounds, it means like upsampling the data to get more data points in a short period of time. I would actually not do this because upsampling the data means not adding information. So this is just interpolation. So I would not just sample up the data. However, of course, if you sample during recording already with a very high sampling rate, then this might already fulfill, of course, the prerequisite for ICA, because then you have more data points for a short stretch of data. Okay, so that's it for the questions, and I would just go back to the slides to wrap up this session. And I have some concluding remarks or some take-home messages for you. So ICA is a statistical method to decompose a signal mixture into its constituent source signals. This method is not specific for EEG, but it can be applied to any signal fulfilling the prerequisites. The main goal of the algorithm with respect to EEG source signals is to maximize temporal independence. After unmixing, the components can be back-projected to channels, whereby the inverse weights can be visualized as topographic maps. If you do not include a component in the back projection, this is equivalent to deleting this source signal from the signal mixture. This is the main idea behind ICA-based ocular correction. Importantly, the data has to be adequately preprocessed to make sure that the decomposition results in valid components. Therefore, also do the quality check. In the end, ICA results need interpretation, and this is up to the user. However, there are algorithms that can be used as little helpers to base your decision on statistical properties, and Analyzer offers some of these in the Ocular ICA transformation. Okay, just some further reading. So there are these books here that are very specifically about the ICA analysis, but very general. So it's not about removing ocular components. So this is really also, some of them are very mathematical. This is really about the method. But if you want to learn more about ICA as a method, I can recommend these books. If you rather want to learn about ICA on a more specific perspective, these two chapters here are quite interesting in these two books. And then there are also some nice articles that I would recommend. Also, the articles that I mentioned earlier in the presentation are in these references here. And finally, we also have some material ourselves. So of course, all the transformations I showed are covered in detail in the Analyzer user manual. And we also have two brain product support tips that appeared in press releases. One about Ocular Correction ICA specifically, so the second part that we did today, and one about independent component analysis in general. So it's the demystified article that should again uncover all the mysteries of ICA. So this follows very much our webinar today. And with this, I want to thank you for watching this webinar. In our Brain Products webinar channel, you can rewatch this as often as you want, and also you will find other webinars here. And of course, if you have any questions about the content of this webinar, or you have questions regarding your own data in ICA, please feel free to contact us at support@brainproducts.com. And with that, I want to say thank you again. Goodbye, and see you around in our next webinars.